Hi everyone, and welcome back to another video. It's me, Carolyn, and today we are going to be looking at what the sampling distribution for the mean, so the averages, looks like. And I'm going to jump right into the guided notes on this one because I have a lot of it written down for us to look at already as soon as it unfreezes from the previous thing. So we are in chapter 8 and we're looking at some sampling distributions. And we're going to see that it is very closely related to what we did in chapter 7. Hence the reason I kind of pair these two chapters together when I'm teaching. But a lot of times we're going to be looking this time not at what a single person, where they sit, what is the probability that a person does this, or a can looks like this, or a bag of chips has, or a bag of chocolate cookies has this many chips. We're going to be asking ourselves questions like, what is the average of this group look like? Is the average of this group bigger than a value, smaller than a value, or between two values? So a little bit different. We're not going to be asking about a single person, but the mean. So if you were looking at our probabilities, we wouldn't be looking like, what is the probability that X is greater than 7? Here, we're going to start asking ourselves, what's the probability that X bar is greater than 7? Okay, and for us to be able to do that, we kind of need to know what shape this thing takes on. The nice thing is we do have some very nice results. And hence the reason why the normal curve is studied so much is because of these results. It turns out, and I'm not going to go through all the statistical background on why it does. We're just going to use the results in this class, which makes it a lot easier. But it does turn out that if our original data that we're sampling from is originally normal or somewhat normal or approximately normal, the samples, so these X bars that we start looking at, will also be normal. So that's great. We still have our normal curve, but we even have more. We have that the mean of our X bars is going to be the same as the mean of the original distribution, which should make sense. Because if we have an average out there and we start looking at all these different groups and averaging all these means together, so we basically take a group of 6, take a different group of 6, and we do this for every group of 6 we can come up with, and we calculate those little X bars. So X bar for one group, X bar for another group, X bar for a third group. And we then average, look at what those averages are. So it's like the average of the averages. We should get the same average. Okay. It also turns out that our standard deviation is based on the standard deviation before, but it's going to get smaller. So I'm going to zoom in a little bit here so we can see my notation. So this is the standard deviation of our X bars, and it's equal to the standard deviation of the original data divided by the square root of n. Okay, and the reason for that is because as n gets larger, we're basically smoothing out all of the irregularities. Because if you have someone down that's an outlier, but you all of a sudden throw them into a group of people, they don't have that much pull anymore because their average is going to be skewed a little bit, but it's not going to be a skew. They're not going to be able to skew the entire thing as much because they're not going to be included in every single group. So our standard deviation does get smaller. We also have more. And this is the big, powerful thing, the central limit theorem. I think I need to zoom out a little bit to get it all on one page here. So sorry about that. The central limit theorem says, regardless of what the shape of the original distribution is. So I don't care how ugly it is. It could be the most non-normal looking thing out there. Maybe we have it skewed completely one direction or another. The distribution for X bar becomes approximately normal as this n increases. We still have these two pieces above as well. The thing is we don't have to have n to be super large. It turns out that as long as n is bigger than 30, we will be approximately normal, which means we can use all the normal curve material that we did before. We can use our standard normal curve. We can use our z-scores. We can do all of that all again, as long as we sample more than 30. And this is a lot of times why statisticians harp on how many people are in the group. We want to have a significant number, and so we can do some of this analysis on there. And as long as we're bigger than 30, we should be okay. So we're going to go through a couple examples, not a whole lot, because the steps are very similar to ones that we've already seen. And I don't want to continuously bore you by going through them over and over and over again. But we're going to look at a sample of some football players. So we're looking at the salaries of football players, and they have a mean of $120,000 and a standard deviation of 2,300. And the first question I have here is, how do you think the distribution of salaries for these football players would be? What shape do you think it would take on? What would it look like if you were graphing the salaries for football players? So I'm going to give you just a few minutes here to kind of think of that before I kind of jump in and explain. Okay. All right. Well, the way it would look is if you were to think about how football players are played, we have a lot of players, linemen, defensive people, unless they're really big named people that earn about the same amount. But we also have these few people that are a lot of times the quarterbacks, running backs, things of that nature that are going to be way on the outside. So if you were looking at a graph, you would have a lot of people down in this area. You know, I mean, yes, it's still a lot more than I make, but you'd also have these few people that are way up here. So this thing would probably be, and this is really badly drawn, but it would be skewed to the right, because we'd have these big people down here making lots and lots and lots of money that is going to pull that average up a little bit. Okay. But that's not going to matter. As long as I take more than 30 people in my sample, I can still use the normal curve, no matter how skewed this thing is. Which is nice, because now what if I say I want to know what is the probability that a sample mean of 40 players has a mean salary of more than 121,000. So in terms of notation, I'm looking for a probability that the mean, so the X bar of these 40 people that's going to come into play, is more than $121,000. Okay. Since n is 40, which is bigger than my magic number 30. Again, I'm not going to go into why the 30, why not 32. It just turns out that way. Just go with it. Our distribution is roughly normal. And we also know that the mean is going to be the same as the mean of the original data. So the mu of X bar is still going to be that 120 over $120,000. Also from the central limit theorem, we know what our standard deviation looks like. Our standard deviation is going to be the standard deviation of the original one divided by the square root of n. And I'm going to leave it there. And this information all is possible from the central limit theorem, from the central limit theorem. Good thing we don't have to prove it, we just get to use it. Okay, so this means I can draw a normal curve. Yay! So there's my bell shape. I know the middle is 120,000 right there. We want to know more than 121, so there's my 121. And we're going more. Since it's roughly normal, we can standardize this thing. We can turn it into a standard normal curve. Now, remembering that our Z is our data value or the value minus the mean over the standard deviation. Now, realize we are not talking about X here. We are talking about X bar. So our data value is still that 121. That's the question in play. That's the boundary value. Our mean is going to be the mean of X bar, but that's the same as the mean from before. So that doesn't really change. But our standard deviation for X bar does. So we're not going to be dividing by just the 2300. We have to divide by 2300 divided by the square root of 40. Okay. When I do this on my calculator, you must be very careful to make sure you do it correctly. The way I work this is I get that subtraction first. So I will do the 121 minus the 120. And I get that value of that $1,000. And then I divide by, in parentheses, that bottom. And I come up with 2 point, and I'm rounding to 2 digits again, because that's what my table has. So we're going to 2 decimals. And this is a Z. Okay. And now what I'm going to do is take that Z to my table, 2.75. I have 0.9970, so 2.75, that's my Z. Going to the table, and I come up with 0.9970. My picture's not drawn very well, but that's okay. That's the area from that point on. So to find the upper part, we need to do 1 minus 9970, which is 0.000. So it is very unlikely that we get a sample of 40 players to have, in this situation, to have a average of more than 121,000. Okay. So I know, and I'm not going to do a whole lot of these, but I'm going to do another one just to kind of show you the differences between a chapter 7 where we're talking about one thing and chapter 8 where we're talking about 2, and kind of point out the differences in the wording and things of that nature. So first thing, the only thing that's changed from chapter 7 are the following. We're going to be talking about the average or the mean or X bar of a sample instead of a single item. Okay, so we're not going to be asking ourselves what is the probability that a person, not the we're going to be looking at what is the probability that the average of this group. The formula for standardizing is changed just a little bit, okay? We have to remember that when we're talking about these averages, we don't have the plain standard deviation anymore. That standard deviation has changed a little bit because we're looking at the standard deviations of these samples, not just for a single person. So let's do one problem comparing these two pieces. We'll hopefully kind of solidify some of this stuff. All right, so we've got a tuna can. The weight of a tuna can is normally distributed with a mean of 12 ounces and a standard deviation of 1.5 ounces. And I want to find, first of all, what is the probability that a single can weighs less than 10 ounces? So X itself, and sometimes you'll see this in textbooks, is distributed, and I'll write it in words. Distributed normal, with a mean of 12, standard deviation of 1.5. Okay. Sometimes in some books you'll see that X, and they'll give you this little wavy line. That's to fill in all the rest is distributed. Then they'll use an N for normal, and they usually like to put the mean first and the standard deviation. Okay, so this is your mean, standard deviation, and that is for X. All right, so if I'm doing my picture, still normal curve, because we were told it's normally distributed. Mean is 12, because the mean of a single person's group is going to be the same if we were lumping them all together, looking at samples. 1.5, that changes our shape. We talked about that earlier. The smaller the standard deviation, the more pushed together and squished it is, so it's going to be a little bit taller and skinnier. Mine tend to look all the same. That's okay. And we want to know less than 10. So 10 is on this side, and less than it goes this direction. Okay. Now, when we standardize this to find our z-score, we'll do our 10 minus our mean, because we're talking about a single person, divided by that 1.5. If you wanted to, you could be taking this and divide it by the square root of 1, because that's our sample size. And then you'd be using the 1 formula all of the time. But the square root of 1 is 1. So, all right, so I'm going to take that 10 minus the 12, divided by 1.5. It will be negative because I am smaller than the mean. Again, I round to 2 decimals. So I get my z to be a negative 1.33. That's kind of like taking this to a 0. This is going to go to a negative 1.33 on the z scale. And it reshapes the curve a little bit so that the areas all stay the same as well. So we take that to our table. I need to be on the negative side, negative 1.33, 0.0918, 0.0918. So if I were talking about what percent, 9% score have way less than 10 ounces. I can do problems unstandardizing these guys. Don't do a lot of unstandardizing with the averages, but you could. It's a little bit messier because of that, that piece down there. All right, so now this one, it says, what is the probability that the mean of 10 cans, so now we have 10 cans, this is the sample size. Should have chosen a different number other than 10. But we want to know it has an average of less than 10 ounces. So we want to know what is the probability that X bar is less than 10. Here we were looking for what is the probability that X is less than 10. Slightly different question, because we're looking at what is the probability that the mean of these 10 cans. What is the probability that a single can or a can? I put the word single in there just to emphasize it. Now, we have to be a little bit careful because when we're looking at X bar, we have to make sure that we're still considered normal to keep moving forward. We don't have more than 30 cans, which would automatically put us at normal by the central limit theorem. But we're still okay because our original distribution was normal. Was normal. The distribution for X bar will also be normal. also be normal. But the mean and the standard deviation are, well, the mean doesn't change. The mean of our x bar is still the mean of our x, which is still 12. Okay, but the standard deviation for x bar is the standard deviation for x divided by that square root of 10. So we will have that 1.5 over the square root of n being our sample size. Okay, not the 10 that's here, but the sample size. All right, so drawing my picture. There's my 12. There's my 10. We want to go smaller than 10. So again, we are going to find my z. And be my 10 minus the mean divided by my standard deviation. Since we're looking at the average, we need to use this as our standard deviation. The same formula, it's just that our standard deviation has changed. Okay, being very careful, taking the 10 minus the 12 and then dividing by that whole piece, I get a negative 4.22 if I round to 2 decimals. All right. Now, if I look at my table doesn't go that far. But the smallest number I have is a negative 3.49, which is, and that's the area to this guy. So that's 0.0002. So if this is negative 4.22, and if I have an, I'm just going to put it on the z scale, a negative 3.49 is going to be on this side of it. So the area there is 0.0002. All I can say is that our probability is going to be less than 0.0002 based on the information I have from the table. Now, some tables will go smaller, but when we're talking about something that's almost zero, we don't need to go much further than that. So I would probably just say it's going to be less than 0.0002% or 0.02%, but a very small probability. So very unlikely that we would get a sample of 10 cans to be less than 10 ounces. And a lot of times these sorts of problems are what are used to determine whether or not machines need updating. If they need to be recalibrated, they will kind of start weighing things and saying, okay, is it filling these cans correctly? Is it weighing what there should be weighing? And if they aren't, if we're finding them to be too heavy or too light, machines are then recalibrated. So they do find these outlier kind of piece areas and work with them. And so stats is used in the manufacturing areas all the time. But that is pretty much 8.1. And our next section is going to look at things a little bit different. So we're going to go back to an old friend, the binomial, and we'll look at him and we'll see how he can be related to the normal curve. But that's in the next video. So have a fabulous day, and I'll see you in the next video.